Yeah, I muted it. Oh my God, I forgot that I muted it. I'm sorry. Like,
Hi, Heather.
hey, Dmitry. Okay, so I had muted it a while ago and I forgot. Okay, so let's get started. So I want to quickly explain why Dmitry exists on the screen. I feel like slightly guilty because the U.S. government is holding on to his passport while they're processing his visa, and they've been like holding it for many months, like longer than they're supposed to. So despite the fact that he really actually wanted to be here, thanks to the U.S. immigration system, he was unable to actually travel anywhere. So it was very nice of him to actually get up, because he's in San Francisco. It's like, what time is it? It's like 6 in the morning, 6:30 in the morning. So he's like real trooper right now for giving a talk in London at 6:30 in the morning. So that was really nice of him. But what's really cool is that we can do the questions and answers just like normal. So we're going to walk around with the mic if you want to ask him questions afterwards, and it is patched right through to him. So with the exception of somebody not standing here, everything else should go according to what you're used to. So I will stop talking now. Dmitry, go ahead.
Thank you, Heather. Can I be heard? Can you hear me clearly?
Yeah, it's all
Awesome.
good.
Okay, so hello, everybody. Again, as Heather said, if you have any questions, please ask at any moment during the talk. And let's get started. Okay, so this is a talk about gradual typing for Ruby at scale with Sorbet. Before we go into the details, I want to give you some amount of background. So first of all, some introductions. Dmitry, I finished a PhD with Martin Adursky, working on Scala mostly. Most of my research has been around how to design a type system and a compiler so that it's both maintainable and fast. And my thesis effectively was the compiler for Scala 3. Now, the other part of background is, well, Stripe. Stripe is a company where I work. Stripe is a platform that developers use to accept payments. We operate in 32 countries with millions of businesses worldwide using us every day. Billions of dollars are processed annually, and more than 80% of American adults bought something on Stripe in 2017. We have more than 1,700 people in 10 offices around the world, and as always, we're hiring. Now, more specifically, I work in developer productivity at Stripe. The developer productivity at Stripe is a team that's responsible for anything that happens for developers between the moment they create a Git branch till the code reaches prod. This includes testing, the way you work with code, your development environment, core coding abstractions, language tools, documentation, platform teams. Overall, if a Stripe developer is having a bad day or feel unproductive, it's our problem. We own everything that's unknown, and we own the developer experience at Stripe end-to-end. Now, Ruby. Ruby is a primary language used at Stripe. Stripe uses a subset of Ruby enforced by syntactic rules implemented by Robocop. Unlike most other companies who use Ruby, we do not use Rails. Most product code at Stripe is in monorepo, and that's intentional, with Stripe having 10 or so macroservices and only a few microservices. And new code mostly goes into existing services, and mostly in those 10s. To give you some perspective on the scale of engineering, Stripe has hundreds of engineers, thousands of commits per day, and million lines of code. The top languages at Stripe are in order: Ruby, JavaScript, YAML, Python, Scala, Go. The next language is Bash, which is 2%. So this gives you some perspective of how development in Stripe is organized. The majority of engineers and majority of code at Stripe is written in Ruby. Now, before I start presenting Sorbet itself, I want to say that this is a result of collaboration with a lot of fine folks. Jeff Foster has been doing research on how to type Ruby for more than a decade, written in Tufts and now in Plum. Charlie Somerville, who works at GitHub, wrote the Ruby parser that we're using. Sutaru Matsumoto, this CTO of Cider, is an author of Type Checker of Steve that did the original exploration for how to type common Ruby code. Mame-san worked on Type Profiler that allows you to infer types for existing code, and Matt's created Ruby. He's the BDFL of Ruby. Aside from them, who are the working group on types for Ruby 3, we also have a lot of contributions from Shopify, Coinbase, SourceGraph, and Kickstarter. As we have contributions from them, you can say that Sorbet is open source. Before open sourcing, we spent more than 3 months long with a closed beta with more than 30 companies to make sure that we can be adopted by other companies than Stripe. And if you're looking to have a successful launch, we believe that this was the biggest thing that contributed to a successful launch of Stripe. You can find documentation on Sorbet at sorbet.org, and there's also a demo site which you can open, which is sorbet.run. Heads up, if you're opening from a mobile device, substantial amount of functionality will not work. But if you open it from a desktop browser, you should have it autocomplete, jump to definition, find a reference, all the IDE tools should be present there. Now, let's get into the body of the actual talk. So, as we were deciding a type system, the most important thing was which problems does it solve. So in order to drill down those more specifically, here is the summary of the kickoff email that we wrote internally at Stripe. So the goals are eliminate a whole class of errors. We know that this is not an experiment because we've seen it successful in other languages. We want to make us more confident in our code mods and refactoring tools used at Stripe. We want to force our developers to think more about the interfaces that they provide to each other, and want to make the code more readable. As you can see, the explicit goals of our projects were all human-driven. Want to make sure the code is easier to read and easier to write. And this is compared to a different design of a type system that would have been for compilation or for static reasoning. It was not a goal of our type system to be rigorous. It was not a goal of our type system for the sake of being rigorous. It was not a goal of our type system to be used to do optimizations. It was the goal of our type system to make it easier for users to reason about this. Here's the approximate timeline of the project. We started the project in October. We have ran experiments before November. We rolled out the first implementation of it to be used by our team internally in around February 2017, and we had a global rollout in April. I'll focus on some specific areas of those, starting with type syntax. So before we go into the type system syntax, it's important to know that Stripe had already a runtime type system a year before we started working on static one. It was a way to indicate that your method will be taking some values and what do you want those values to be. It's kind of similar to contracts. It was written in Ruby and had around 5,000 methods which were typed, which were the most critical methods. The original type system used the first syntax in the slide, which is standard method, where you indicated that if you're taking an argument called bar, it has a type integer, and you're returning a string. Over time, we iterate over multiple iterations of the syntax, and it was made possible because we have a monorepo, which allowed it for us to do whole world refactorings and do substantial changes to syntax without stopping our users. We found this to be very important because it allowed us to discover needs for syntax that we originally didn't know about. For example, the final syntax that we use, the last one presented on this slide, has those curlies, and those curlies actually represent a function, which means the actual body of the signature, the thing that specifies which classes you refer to, is lazy, which allows us to address problems with cycles and the order in which you load classes. We evaluated a lot of syntaxes. We rejected majority of them. Some of them were rejected because they were not better enough than the thing that we had at the time. Some of them were rejected because they're very hard to implement without changing the Ruby VM. So now we'll go more into the design of the type system and what were the high-level principles behind the design. I'll dive into each of them more specifically. So the first one is we're willing to have our users write type annotations. We, in fact, see them as beneficial. We believe that type annotations make code more readable and more predictable. We're here to help readers as much as writers, and we frequently have many more readers of the code than we have writers. So we're willing to optimize for readers, and thus Sorbet doesn't do any type inference on a cross-methods boundary. The second one is some people think that type systems can be too verbose, in particular if those people have been using a language without types for quite a while. And we overall agree with them. There are many type systems that are quite verbose. This is why we want ours to be concise. In particular, in this example, you don't have to specify a type for A. We can infer that it's integer from context. But if you do want to specify the type intentionally, you can also, for the second A, you can explicitly declare that you're intending A to be a string. The next principle is we want our type system to be simple, but not simpler than it has to be. What do we mean by this? As that we're not strong believers in super complex type systems for sake of being over the complexity. They have their place, and we need a fair amount of expressive power to model real Ruby code. But all things being equal, we would prefer to be simpler. We believe that simpler type systems scale better, and most importantly, it's easier for user to learn and understand them. This list actually lists the things that we've been adding gradually to the type system as we found things that by need of our users. So first of all, we started with nominal and gradual type system. Then we added union intersection types to reason about control flow dependency. We added local type inference for the same matter. Then we, in order to type standard library, we needed generic class of methods, and then to type some methods such as clone and dupe, we needed self-types. The next one is scaling. We need the type system to scale in speed, team size, code base size, and time. By time, I mean that we're not postponing hard decisions. Stripe already has a large code base. We believe that we're one of the largest Ruby code bases in the world, if not the largest, and we expect us to only get bigger. So it's important for us to make sure that the tool that makes it possible for people to stay productive today, the tool that today allows them to have fast iteration cycle, will not become slow in several years from now. So to give you some understanding how fast it is and how fast iteration cycle do we want to provide our users, we believe that to have good user experience, the user has to have less than 200 milliseconds iteration cycle. And to power this, Sorbet currently has around 100K lines per second per CPU core type checking speed. We're on multi-core systems, so it's overall the experience for the batch type checking is around 10 seconds or so, while for incremental compilations is under 10 milliseconds. To give you some comparison with other commonly used tools in industry, Java-C has around 10K lines per second per core, which, to be honest, is not a fair comparison because Java-C also does bytecode emission, while Sorbet does not. Sorbet output is effectively just error messages. And Ruby-Cop, the commonly used syntax for enforcing Ruby. Syntactic tools on Ruby has around 1,000 lines per second per core. The next guiding principle is that we wanted Sorbet to be compatible with Ruby. In particular, we didn't want to build any new syntax. Existing Ruby syntax means that we can leverage most of the existing tools, editors, refactoring tools, aforementioned Ruby-Cop, and our point was to improve existing Ruby code base so that it can be adopted incrementally, which means we cannot build a new parser or something and like have half of the code base parsed by the existing parser and half of the code base parsed by a new parser. And finally, we want the type system to be possible to adopt gradually. In order to make adoption possible in our scale, we cannot require all the teams to adopt it all at once. And thus, we need to support teams adopting it at a different pace. So what we've built is that when you just add a file without any annotations, then we have a very basic number of things checked by default, such as syntax errors. But then if you want real type checking, you need to leave a sigil in the file called type2, which is written as type true, which enables actual type checking. Then you have a level called type strict, where you will require all of your interface to be typed. And the highest level that exists today is a type strong, where not only interface has to be typed, but every intermediate value that any method in the file ever computes should also be typed. This was necessary. As gradual adoption was necessary, we had to build runtime type checking, and this example motivates this. Here you have a typed file, which declares a function that takes an integer, and an untyped file that passes a string. Because the untyped file is not type checked, we cannot make sure that the typed file is safe. And because we do control flow dependent typing, if we were to write the code inside foo that tries to verify that a is an integer, we'll discard it as dead code because we believe it cannot be not an integer. So we needed to have a runtime system to do type checking. The common reason is because untyped code can call into typed code, and untyped code can also perform stores into fields which will be read by a typed code. And as aforementioned, the typed code cannot protect itself, as we'll complain that the protection is dead. So the runtime type checking was necessary at launch. And at the same time, we also believe it will be necessary effectively for Wrapper, because you'll always have some kind of library which is external, that's a gem, and that is not typed and it's not being type checked now, so you need to be able to protect type code from it. Next, and the probably most interesting part, is how did we do the rollout? So first of all, what's a rollout? Rollout for us meant getting more people to choose to use Sorbet at Stripe. A stripe Sorbet was an optional tool that you can decide to use in your files as part of Gradual rollout, and we want to make sure that our users feel that the tool is useful for them. We're not going to force them to use it. We're going to build enough value in it so that they see its value for them and they're willing to change the way they work. The secondary metric for this was how many types are being typed. And the third metric is how many values inside the typed files are actually typed. Because our type system is gradual, we have a type that stands for untyped, and thus you can trivially type all the code by having all the values on it being untyped, and it doesn't reduce much value. So going on this, the first perspective you can have in order to move the 2 metric out of 3 is go type all the things. And this was like a pleasant perspective to have, but unfortunately it doesn't work in our case. The reality is our team started with 3 engineers. We're a small group of engineers, and we can't manually do the changes necessary for code to become typed. We needed tools to do this in production, to do this at scale, to apply to 1 million lines of code with a small number of engineers. So we built the following tools. The tools that bridge the gap between static analysis and runtime metaprogramming, the tools that fix common bugs automatically, the tools that find what can be type checked easily, and the tools that find what are the most impactful things to type. And as part of typing the most impactful things to type, we build the tools that make it possible to suggest the types to our users. So the first one, bridging the gap between static analysis and runtime metaprogramming, is arguably the most important, and I need to give some background to explain why. In Ruby, there is a common practice to do metaprogramming. What this means is that in runtime, you'll write the code that defines classes or methods. In this particular snippet, the inject method, given a class, will define a method with a name that returns a value. And by evaluating the snippet entirely, you'll effectively define a method called favorite number on integers that returns 42. This is very hard to analyze with static analysis. And rather than analyzing the static analysis, we built an external tool which makes dynamic definition static. The way it works is we load the entire code base in memory inside RubyVM. Then we walk all the classes to see which methods do they have, which classes do they inherit, which interfaces do they implement, and we serialize this into a file. Then we load the same code base in Sorbet, and we serialize what Sorbet believes is true about this code base. Now we see the reality, and we see what can observe statically. We can compare both and serialize the diff. This diff is stored as something that we call RBI, Ruby interface file, in our code base, and for our code base, it's around 200,000 lines or so. Around 700 more lines of code of similar interface is for gems. And this lists methods that are created dynamically in the runtime, and in order to see them being created, you need to run this code. This made it possible to make sure that Sorbet has perfect knowledge of the world in the sense that it has correct class hierarchy that includes classes that were either conditionally included or dynamically included in others. And it has the complete list of methods that includes methods that have been metaprogrammed into existence. The second one was, as you're typing code, as you're adding new files to being typed, there are some common bugs that you encounter. The most common bug comes from the fact that the type system of Sorbet is not nullable by default, by this I mean that nil does not inhabit every type. In order to have the value nil, which is the Ruby speak for null in Java, you have to explicitly mark this type as null. And a lot of existing code didn't correctly handle all the corner cases where something could have been nil, and thus could have called methods in it. So we introduced an autocorrect that automatically is able to insert something that we call t.must, which verifies that the value that it gets is not nil, and the type system is aware of this method. This was the most common autocorrect, which allowed to type substantial number of code and make it explicit that this code historically before this relied on implicitly not ever getting nil. The second tool was finding type checkable files. As you're doing more and more code modifications, more and more files become type checked. And this tool allowed us to find which files can be type checked today. combining the aforementioned tools, we got to quite a high number of typing by files. But we also needed to do something about making sure that the files themselves internally have values which have types. In order to do this, we built a tool that found most impactful things to type. So in this example, in order to be able to type check both bar and baz, you first need to be able to get the result type of the method foo. So we've built a tool that effectively says what's necessary to have type annotated in order to annotate and to have type for end call sites. And this gave us a punch list, an ordered list of things for us to type in order to get more typing in our code base. We shared this with us, we typed it ourselves, we shared it with our users. And this allowed us to get to high degrees of typing and amplify our effort by typing the things which are impactful. And finally, as you're typing the things which are impactful, we've actually built some amount of global type inference into Sorbet specifically to be able to do suggestions for method return types and method arguments. We evaluate what's necessary to be true for the arguments of your methods for the method to type check, and what has necessary to be true for return type of your method for the to type check. Now, going back into more practical, the other practical side of rollout, which is like talking to real systems, talking to real people, and talking to real code. At this moment, we wanted to find an image that best represents our experience, and that's the one that we found. Stripe processes money every second. Our users rely on us being up in order for them to be able to accept payments and for their businesses to operate. It was not an option at Stripe to shut down Stripe for any downtime to roll out type system. At the same time, it was neither an option to stop the development of Stripe to do typing. From our experience, our code base doubles 2x each year, so we effectively had to type it in flight and be able to type it faster than it grows. At the same time, we have more people working at Stripe, and they operate Stripe today, and it was necessary for us to make sure they have good experience with Sorbet before we roll it out visibly for them, so that they're willing to use it, they find this tool useful rather than burdensome. In order to do this, we had something that we call dork launch. Before making it visible for other developers at Stripe, our team has spent around 2 months observing what would their experience be like. As you can see here in one of the last messages, the master, the most important branch in our repo, at some moment had type errors, which means our tests did not find an error that the type system complained about, which may mean either type system has a bug or tests are imperfect. And as we were developing the type system, in early days, it was pretty common that were bugs in the type system, or we were too strict and we're complaining about the things that our users would necessarily care about. So by having 60 days of the launch, dark launch, and observing what would user experience be like, it made it possible for us to have our internal users have good experience on the proper launch. The second important thing was to give our users escape hatches. The important escape hatches was to be able to talk to somebody. We created a Slack channel in our internal chat where people can go and talk to us about their experience and share either like anything frustrating, or there's something they don't understand, maybe the error message which is confusing. And this gave us a lot of information about how to improve it. It was also very important to make it possible for users to reproduce the error locally rather than waiting in CI. It was also super important to have a workaround. Let's say our type system has a bug, or they have to move fast, and they know that there isn't something that's imperfect, but they have to move up with it. So it was important to have workarounds that allow to silence type system errors. So we built 2 ways to silence them. One is for the static type system, where you can indicate that where you can disable the static type system. This is t-unsafe, where the runtime will still be checking your methods. And the other one is a silencer for runtime type system, which is check false, where the static will continue checking you, but you won't be checked by the runtime type system. And finally, in order to do the rollout, we had to define metrics to track the rollout. The metrics that we originally chose were % of type true files and % of method calls known at the call site. In 3 months, we were able to get to 70% typing by files and around 50% typing by call sites. Here's a graph of how the typeness of file went. The original 20% steady line is our actual dark launch, where we were looking what would be the experience like for 20% of the code base. And then we started rolling it out and suggesting our users to type their code. And as you can see, in around a month, our users have willingly accepted our PRs to type majority of their codes. Those PRs were generated by aforementioned tooling, and those PRs were approved by the teams who maintain their systems. And since then, in order for their PRs to pass CI, they were required to follow rules imposed by the type checker. For resolving calls, this is a much harder metric to move because you need to know which methods to type. And over around 3 months of work, we got through from around 25% to around 50%. The interesting number is where this 25% come from. 25% is the amount of typing that we got from having types for standard library rather than our own code base. We actually took them from RDL, the project that Jeff Foster worked on in academia. They had good annotations for standard library, and they were tremendously useful for us to get our project started. Today, at Stripe, our code base is around 85% typed by files, is around 80% file typed by call sites, which creates enormous amount of confidence in the code base. Entire classes of tests have been eliminated, and new tools have been built, such as autocomplete, jump to definition, and things like this. This graph represents the way how number of human authors grow. And this was an important metric for us to track to see whether users find writing things pleasant for them and whether they find it useful from their personal experience, rather than us writing them with tools. Now, going to practical experience from feedback from our users. It was explicit goal of us to build a practical type checker for Ruby, and we're linking this to our experience at the time at Stripe and now at other companies too. There are some bugs that we found in process of rolling it out that slipped through CI and code review, and finding those bugs much faster and with shorter iteration cycles is a strong indicator of whether it's a practically useful type system. One common type of bug is dead code. Here, an interesting thing to note is that foo is assigned in both cases in this example. But then if you take this common example where somebody who's coming from Python or something on a language where 0 can be falsy, they can think that the else branch ever executes. While in Ruby, all integers are truthy. So in this later snippet, there's else branch which is dead. We found that during the rollout, that a substantial amount of code was written for cases that can no longer be possible in our production, that can no longer happen. And deleting substantial amount of code created substantially reduced the burden of maintenance for a lot of teams. Another common bug that we found was typos in error handling. Error handling is the code that rarely gets executed in either tests or production. It's very hard to cover all the error cases in tests because it requires you to find all the combinations of them in particular. And in production, hopefully, error handling happens rarely. So we found tremendous number of even simple bugs in error handling. Like in this case, the exception that gets processed is parse error, while the real error is parser error. Or similarly, argument error is not a method, it's a class. So in this specific snippet, similarly to Python, people didn't expect that they have to write new. And we found a lot of similar bugs in a lot of places, and they were super useful to reduce number of tests which needs to manually trigger them and verify that it works correctly. As mentioned earlier, a very common bug is nil checks. Having strict nullibility found a bug in our endpoint that wasn't handled by API requests. This specific endpoint takes a hook ID from the user and updates it in our system. The load method here is actually able to return nil if the ID that user passed didn't exist. which will create a user visible error. Having a type system here allowed us to make this error much nicer, where we'll get a proper error reporting for user, where we'll give them error that rather than just having a breakage error, we'll have them specifically that the ID didn't exist. And also a common error that we saw was incorrect pattern matching, where similarly to other kinds of dead code, you write a pattern when you expect things to happen, but they may not. This is a funny error in particular because the way how Ruby evaluates this, the OR will be evaluated before pattern matching even starts. So the first value, the first expression that will get evaluated in Ruby here is after you evaluate transaction, you evaluate stripe : charge or stripe : refund. Because stripe : charge is always truthy, this branch will only match stripe : charge. Now, other than just code examples, one more way to get feedback is user response. And Sorbet, both internal at Stripe and in other companies, had great user feedback. We got a lot of great feedback from our users, which, to be honest, was based from modulating what would be their experience like personally for 2 months. We've tried to make the errors beautiful. We tried to make them have feedback really fast to make sure that they were a fast iteration cycle. We found that a lot of users have been gradually reducing their usage of tests and replacing them with things that type system can prove statically because it gives them both faster iteration cycle and better editing cycle as the IDE will be able to find it early. We found a lot of cases where we're able to stop production incidents either before ever happening or make sure that they never happen in production after it was a way to remediate these incidents and existing incidents. And similar experiences have been seen by other companies, by Shopify, by Kickstarter, by majority of companies who tried it. So in closing, here's a set of areas that we covered. I'm super happy to take questions for you about them and others. If you want to reach out to us, there is an email called sorbet@stripe.com where the entire team is responding to you. You can find the documentation for Sorbet at sorbet.org. You can find a demo at sorbet.run. Thank you for listening, and please ask your questions.
Let's thank the speaker. Okay, so I hope you can hear me, Dmitry?
Yes, I can hear Heather.
So we have a mic in case anybody has any questions. Anybody? So I have a question, actually. So I mean, it's like sort of towards like you were showing like how this thing has helped you find a bunch of bugs, like when people were mistyping like the names of exceptions or something, right? I mean, this maybe sounds silly, but like there's probably a group of these kinds of situations where you could probably totally synthesize a fix, right? I mean, I know that like this is a compiler and not like a program repair tool, but like, I mean, it seems like these are rather like innocuous, I mean, not so controversial sorts of things that you could probably synthesize fixes for and at least provide people with diffs or something, right? I mean, I don't know, like probably you want to just keep with like, a type checker and a compiler and all of that, but like I was wondering if, this kind of tooling was ever interesting, especially for pretty big code bases.
Yep. You're asking exactly the right question. The only way we're able to roll out and actually fix all those bugs is by automating this. So as you see here, we're actually suggesting you what we believe you meant there. In this specific example, we believe that you meant parser error. And actually, there's a flag to pass to Sorbet to automatically fix all the errors that Sorbet can automatically fix. Yeah. It was instrumental for the rollout, so your question is on point, and it's definitely necessary for the code base of sites like ours.
Yeah.
A small group cannot fix them all by hand.
Yeah. Anybody else? Oh yeah, sorry. It's a question.
I wonder about the exact interaction between static and dynamic checking, which you mentioned, I think, around slide 27. Like, is it to make the type system sound, or like, what was the design goal? is soundness important, for example?
Great question. So, first of all, it helps us to have soundness and control, where, for example, we model arrays as covariant for similar reasons for wide JavaDocs, which means, well, our arrays aren't sound. The thing that we do that, to the best of my knowledge, no other runtime type system does, is that we actually will go into your array in runtime and verify that all the values in it correspond to the type written on the signature. So the runtime type system indeed helps a lot with soundness because it verifies that we do not encounter unsound behaviors in production. But to be honest, we expected this to be a problem, but it didn't end up being a problem in practice. We ended up with a type system that in practice is almost always sound, and in order for it to be not, somebody has to effectively intentionally try to write this. Even with the size of the user base that we have, we very rarely encounter this, like once every half a year or so. The case where it ended up being super useful in practice is the cases where you have untyped code, call typed code, violating the requirements that the type code requires from the caller. So in this example, for example, the caller, the definition requires you to pass an integer, while the caller passes a string. So the caller misuses the method. And we found this to be super useful, as when you're writing signatures and you're writing down that has to be true, which is effectively your contract with your users, to make sure people do not misuse it. This creates this writes down and before implicit agreement where who owns the case where you pass an unexpected value. While before, sometimes the implementers of the method throw like a bunch of code to handle common misuses. Well, now it's responsibility of the user to correctly use the methods, and this is explicit in the way we organize work between library authors and library users. Thank you for a great question. And again, this was super instrumental in making sure that the type system works in practice. So, yeah, if you're working in a Gradual type system, runtime components, this from our experience are super useful. Thank you.
Cool. Anybody else? Oh, you've got a question. Go for it.
Yes, quick question. Why were you typing entire files as opposed to allowing some parts of the file to be type checked but not the others?
Yep, great question. We had this discussion for quite a while internally. For flexibility reasons, we can't do this per method. But what we found is if you do it per method, the expectations of the users when they expect the code to be safe, firm, where the safety is enforced by type checking, they don't build a good intuition because you give them too much flexibility and like having one method be type check and another method in the same file be not type check, it actually makes it very hard for them to rely on it. What we found is that during the original rollout, having the graduality of the typed file was possible for the rollout sake, and we can like move the functions across files if we need to. If there's like some function that's really horrible and makes a file untyped that otherwise would be typed. And at the same time, it allowed users to build intuitions of whether they're safe or not. Since then, we actually built even more layers of Stripe where you can specify that entire subfolder requires all the files in it to have at least specific type level, which helped our users even more with their intuition that if you're in this part of the code base, you're guaranteed to have everything typed. But if the rollout had been much harder, the version we're proposing, where we'll be typing on per method basis, was an active opportunity that we discussed as an option to have even more flexibility in case rollouts needed to be even more gradual. Thank you. That's a great question. Thank you.
Cool. Thank you. I think that's all we have time for, so let's thank the speaker.
So everybody, thank you for organizing. Have a great day and enjoy the conference.
Yeah, thanks, Dmitry. Thank you very much. You have a good day.